So let's now go further and add a convective term in it. So it happened to be the convection diffusion class of equations. Okay, so we try to create the solver for convection diffusion class of test case, and for that let's start adapting the solver what we already coded, this one. Okay, and from that we try to create a new solver, even though that solver is available in the release version, but don't adapt straight away, we create our own new solver. Okay, so that is the idea. So let's go to the coding area. Okay, so let's add up this particular solver. Okay, and we want same name. We say my convection diffusion form. Okay, so my convection diffusion form, and let it be a number 4. Fine. So first set the C file with the same name as a my convection diffusion form. Okay, immediately. Okay, so this folder we have to delete that. Let's open both the files. Let me close everything. So let's set the name inside the Mac folder as a my convection diffusion form. Okay, so we are set with this. Now first, before we go for further change, let's compile this solver. Okay, OF 3.0x clean.all wmac. Okay, so we are set with this. Now let's open this file, in fact both the files. Okay, so here now if you see, we require the convective velocity as well. So that convective velocity is our vector volume vector field. Okay, and if you want to add up the syntax, you can add up the syntax from the release version. So let's go here, solver, let's say incompressible ICO-form. Okay, let me open both the things. Okay, so let's say create field. Here we have a read a this thing. Okay, so same thing we set here. We say that let's read the field U, must read auto write. Okay, so with the help of that we able to set U and V. T is already there, this is nothing but dt, that is also we already have. Okay, now we are creating the velocity field, so we must also create the is flux as well. Okay, so create phi, at the end you must have this inside the create field.h file. Okay, now we are set with all these things, so let's close this. Now go to the main solver. Okay, so we have this, but along with that now we also require the current number if you want to check what is the current number. Otherwise you can skip that, but it is better to have a current number always here. So I am adapting that as a current number. Okay, till we are working with the simple loop, but if later on we try to convert in terms of the piezo loop as well, so let it be right now as a simple loop. Okay, what else we needed? We required this one term that will take care of our convective part. Okay, so let's add up this term from here and keep it here. So this is how we able to manage this particular thing. Okay, so we are set with temporal term, we are set with the convective term, and we are set with the diffusion term. So convection, diffusion, all the terms is available. This line supposed to be goes outside of this while loop, because we are not updating the velocity more often. Okay, so it unnecessarily we supposed to load the solver to calculate the current number at each iterations. Is better keep it outside. Okay, along with that, okay, we copied this line, but here is u, so it's going to fail the compiler. Okay, so better we go with the this one. Okay, so now let's I think it's set, so let's try to compile the solver. Okay, so let's say wclean wmac, so we are set with solver. Okay, so again what we did in the create field, we adapted the u velocity, so we're going to read the u velocity. Okay, but we're not going to change the u velocity, we just reading. Okay, and then transfer property anyway we have. Now because we have a u velocity, so we must create the flux out of it. Okay, so create phi, and then inside the main solver we calculate current number based on the velocity. Okay, and then we adapt one line that is required for our convective part inside the solver. Okay, and the rest are almost same. With the help of that, we able to compile this test case. Okay, so now let's try to simulate very simple case for based on this. So what we have a one, let's say domain 0 to 2, 0 to 2, we fix the mu. Okay, and then we have a we specify u and v, and we try to look at the convection of this source as a t has a different value. Okay, and let's see how the this particular let's say t equal to 1 portion try to move inside the domain, and for that we say in the streamwise direction we're going to specify the periodic boundary conditions. So that is the idea behind that. Okay, and we fix the delta x and delta t. So for this, let's try to create the test case. Okay, so let's close this. Okay, so in test case we required the test case for the simulation of this class of things. So let's add up from the two-dimensional test case. Okay, whatever we have. So in the Laplacian we have a 2D. Okay, so let's try to add up that case from here. Okay, and then we try to modify it based on our requirement. Rename it 004. Okay, and we supposed to give the same name whatever we have here. Okay, so 2D system, let's first think about the block mesh. Okay, so inside the block mesh, what is the domain we required? In x and y we required the 2. Okay, so in x and y we require the 2 as a domain. So in x direction 2. Okay, and in the y direction also we required the 2. Okay, size we are fixing as a 200 by 200. Okay, so we have a delta x equal to 0.01. Okay, and what else we required? In the streamwise direction we required the periodicity. Okay, so for that let's add up the few lines from the other test case where we already have a periodicity line. So inside this, if you remember, in the okay, not here, we have one test case where we have a periodicity yeah, wave equations. For wave equations, if you remember, we specify the cyclic boundary conditions, okay, or periodic conditions at the inlet. So let's add up this from this side, okay, and fix it at a x min. We have a cyclic and neighbor equal to x max. Same way we have a cyclic here, okay, and the neighbor is x min. So in the x directions we are creating the cyclic BC, okay. Top and bottom, let it be a patch because we want to specify the slip boundary conditions, okay. So here and here, let it be a patch BC, okay, because based on this we want to specify the slip condition over there, okay. So that's why I am specifying that conditions, okay. So now let's go to the area where we want to calculate the, so here OF 3.0 block mesh, okay. So let's first check the mesh, how it's look like. So we have a cyclic boundary in the x directions, okay. So let's check that also. Here cyclic we specify in the x direction, okay. So let's, in the x direction we require the cyclic. So let's now fix the 0 folder, then we add up few more things. 0 folder, okay, in the x direction we have a cyclic, okay. Here we have a slip, okay. So we have a cyclic and slip, otherwise front and back equal to empty, okay. So we are set with this, but along with this, if you look at here inside the create field, we also reading the u, okay. So we have to add up the velocity field as well. So go to the tutorial, let's say incompressible icoform cavity, and add up this u file from here to here, okay. And then let's add up the boundary name from this area to here, okay. So in what we required, we say that in the x direction cyclic, y direction cyclic, okay, but we supposed to specify the velocity, okay. So that we go towards the initialization part and we going to specify the velocity, okay. But here we need not to specify anything because fine. So in the initialization field we try to specify the velocity based on our requirement, okay. So that is what we're going to do, okay. So I think boundary condition wise we are set, okay. So let's look at the, okay, fine. Now we are set with the boundary conditions, but we have to set the initializations. So for that, let's try to add up the funky set field, okay. So let's say funky set field in this area, okay. Try to create the funky set field, okay, and as a t, okay. Now we supposed to specify certain conditions, okay, so that we have a this value. So if let's go to the para form, okay. This is our domain. Let's activate the axis, okay, first. So axis we have, okay, and okay, inside the block mesh we have a converter, so I don't want to convert or domain. So first let me again run the block mesh, okay. So fine. So 1 1 is our center, okay. So from this domain its center of this is 1 1, and from 1 1, let's say this corner is 0.5 away from the center in all the directions. So 1 1, then this goes as a 0.5, and this is goes as a 1.5. okay, so the corner, this is in x direction 0.5, and in y direction also 0.5. Same way this one is in the x direction is 1.5, okay, and in the y direction also, let's say 1.5. okay, so like that way we try to define the funky set field. So let's say condition we set, so we say 0.5. okay, so y is okay, so our condition is what, any y coordinate that is more than 0.5 and lesser than 1.5, that is in the y direction. So any condition that is more than, greater than 0.5, okay, and lesser than 1.5, in this we try to add up this. Same way in the x direction we say point x is greater than 0.5, okay, and x coordinate is less than, let's say 1.5. okay, for that, okay, we can say that the value equal to this field is equal to, let's say 1. okay, so that is what we want at the beginning. So let's what we can do, inside the 0 folder, let's create the backup for both of them. okay, so Control C, Control V, let's say org, okay, because after initialization if you want to come back then it is easy. okay, so now let's say funky set field and time equal to latest okay, what it's saying, putting 1 into the field at t, t does not exit and created type t. okay, let me check, field is t, correct, okay, and let's expression is 1, no problem. T is a volume field, uniform 0, so block mesh, time equal to 0, let's say, yeah, fine. okay, so now let's check paraform. What we want u field. So this is how we able to manage this field. If you think it is a very bigger in size, then you can shrink this, let's say 0.4, okay, greater than, let's say 0.6, okay, and less than 0.4 or greater than 0.8, okay, 2, 8 and 2, let's say. okay, so this is the field we are setting for this. okay, so before you run it again, so let's say cp 0 folder t org goes to 0 folder t, okay, and then run the funky set field. okay, now just check paraform again. So this is fine. So almost it's okay. Now we also supposed to set a u field. Okay, so let's now set the u field. So let's set the u field. Okay, so if you want to set the u field, we need not to do too many things. As a initialization level, only we say that u equal to 1. So with the help of u equal to 1, when we try to run it, it try to add up the velocity in all the internal cell equal to 1. Okay, so it's going to add up very quickly, so no worry about that part. Okay, so now let's go to the our these 3 files and have an idea what we have. So in the here we are working with my diffusion form, so it is better to in the here we can add up the same name. Okay, I think we try to add up this file from the other folder, because this is belong to the steady state solver. Okay, so whatever we run for wave equations, okay, from there we try to, okay, or maybe OpenFOAM we try to add up this file, so it is very easy in that case. Okay, so tutorial, okay, in compress or maybe basic tutorials, transport. Okay, in this also we have this file, so let's add up from here. Check all 3 files. Okay, so this I change it, so that's why it's showing. Okay, so in case of the scalar transport, let's say we are working with our own convective diffusion form. Okay, start time, end time, okay, delta t and writing interval. Okay, so at present we have to work with the delta t equal to 0.1, so accordingly we change it, and writing interval, let's say every 10. Okay, and let's run for something like 5 seconds. Okay, then scheme wise, okay, so scheme wise we don't want steady state scheme. Okay, so we have to add up the scheme as an unsteady scheme, so that is available in OpenFOAM. Pick up any tutorial. Okay, scheme wise you have Eulerian scheme, you pick up from there. Okay, so orthogonal corrections we are using because our mesh is orthogonal, so I think it's not a problem. So let's see my form. Okay, dt is undefined in the directory. Fine, so let's go to the area here, transport property. So in case of this we want dt and the value of dt equal to 0.5 only. Perfect. Let's see again. Wrong token, where transport property dt file. Why? Okay, so let me check from the basic transport property. Okay, so dt, sorry, we have syntax error. Okay, so dt and dt 2 time name is required, and we required this value equal to 0.5. Okay, fine, so let's set with this. So this keyword is missing, so look, when we add up few things from other tutorials, so few errors we get it. Okay, so and then we have to resolve this error based on the output. What it's saying, keyword divergence of phi t is unassigned inside the system fv scheme file. So that means this particular entry is not available in the fv scheme folder. That is correct here. Okay, so we supposed to give this entry. Okay, so that was missing. Now let's see. So it's working now. So we run for 5 seconds. Okay, now check how exactly the scalar transport of that quantity is appearing. So here is the t. Okay, it's almost diffuse. Okay, because of the diffusion characteristic, and it is a periodic flow. So look how it is diffuse, be able to see very quickly. Okay, so that concentration T is propagating inside the domain. Okay, and it's diffusing in nature. Okay, so if we try to turn off that diffusivity, okay, what it means, if I say this value equal to 0, okay, then just check again the simulation we try to run. So this time we say diffusion equal to 0, so it is like a pure convection. Okay, so no diffusion at all. It is now more like a pure convection. Okay, without any diffusion. So this is now pure convections without any diffusion, but whatever we are seeing the diffusive nature is because of the numerical diffusion. Okay, so you can, so now we don't have a diffusion present, but whatever this diffusion we are seeing, it is because of the numerical diffusion. Okay, depending on the schemes and all this thing, we can see this class of variations. Okay, so this is how one can very quickly adapt or develop the solver and create the test case. Okay, so this is very simple example about convection diffusion class of equations. Okay.